All right, welcome back to IDIS 343. Up to now, we've been in the EOQ world, where demand was known and steady. Now we will basically assume demand is a random variable. Here's the plan. We'll start with what uncertainty even means, then the single period news vendor model plus a couple of extensions, then lot size reorder point systems, the Ch4 systems, service levels inside those, and well, periodic review SS policies. Okay, now when we say there's demand uncertainty, we just mean demand is a random variable, something defined by a probability distribution rather than a known value or values. In practice, we kind of lean on the normal distribution, which means we really only need two numbers, the mean, mu, and the variance, sigma squared. And on the slide, there's that classic bell curve, symmetric around the mean, with roughly 68% of the area inside one standard deviation, and basically everything inside three. All right, real quick refresher on the normal, just to get us on the same page. It's continuous, bell-shaped, perfectly symmetric around the mean, and the area underneath equals 1, basically all the probability. The mean sets where the center sits, the standard deviation sets how wide it spreads. Look at the right-hand picture. The tall, narrow blue curve has a tiny variance, the flat gold one a big variance, and the green curves just shoved left because it's mean moved. Same family, just a different shape and location. Now, when is it okay to ignore the randomness and just treat demand as known? Two cases, really. First, when the variance is small relative to the mean, the wobble, doesn't matter much. Second, when the problem is already complex enough that forcing randomness in would make it basically unsolvable. Back in the known and constant world, total cost was G of Q equals K lambda over Q plus lambda C plus HQ over 2, and the economic order quantity is Q star, the square root of 2K lambda over H. But once demand varies period to period, the cost itself becomes random, so our objective shifts to minimizing expected cost. And the law of large numbers is what makes this hold. The law of large numbers in this context just means that as we observe demand over a large number of periods, the average of observed demand will get closer and closer to the actual average demand. All right, let's ground this in the book's example 5.1. Every Sunday, Mac runs a little newsstand and buys copies of a weekly called The Computer Journal. He pays 25 cents a copy, sells each for 75, and leftovers go back to the supplier for 10 cents. Now Mac's careful, he's logged demand every week for 52 weeks, and that count includes customers he couldn't satisfy, not just copies sold. And honestly, when you stare at those numbers, well, there's just no pattern, it's noise. Exactly the kind of demand, that needs a probability model. Okay, here's that same 52 weeks now drawn as a frequency histogram. The horizontal axis is the number of copies demanded, 0 on up past 20. And each bar's height is, how many weeks that demand showed up. You can kind of see it humps up in the middle around 9 or 10 copies, then thins out toward the tails. It's lumpy, it's irregular, but the overall shape is already sort of whispering bell curve. Now from that histogram, we can build an empirical probability distribution. You basically just divide each frequency by 52. For example, demand is 10 journals twice, which makes the probability of 10, 2 over 52, about 0.0385. It works, but it's honestly kind of clunky. You'd store the full history for every item, and here, that's 23 separate probabilities. Other items get messier. That's why we usually approximate it with a smooth continuous curve. And, the normal distribution is the go-to distribution for inventory. All right, the normal distribution needs just two parameters, the mean and the variance, and we estimate them, right from the data. The sample mean, D bar, is just the average of the observations, and the sample variance, squared, is the sum of squared deviations over n minus 1. For max 52 weeks, that's a mean of about 11.73 copies and a standard deviation of about 4.74. And on the slide, that smooth bell sits right over the jagged bars, and honestly, it tracks them nicely. Now, you might figure Mac should just buy the mean, about 12 copies, and call it a day. But something's off. I mean, think about the two ways he loses. If a copy doesn't sell, he's out 25 minus 10, which is 15 cents. But if he runs short and turns a customer away, he loses 75 minus 25, a full 50 cents. The penalty for being short is, much bigger than the penalty for having extra. Stock only the mean, and he'll stock out about as often as he overbuys. And our gut says order more than the mean. Question is, how much more? Okay, let's set the model up cleanly. One product ordered at the start of a single period and, only good for that one period. Two cost numbers do basically all the work. C sub O is the overage cost, what each leftover unit costs you at the end. And C sub U is the underage cost, what each unit of unmet demand costs you. The decision is Q, how many to buy up front, and the goal really is to pick the Q that minimizes expected cost. That's it, two costs and one decision, All right, now we write cost as a function of both the demand D and our order Q. Picture the two cases, If Q lands above demand, the term max of Q minus D 0 grabs the leftovers and we pay overage. If demand lands above Q, the term max of D minus Q 0 grabs the shortage and we pay underage, Only one can be positive in a given week. Stack them together and cost is G of Q, D equals C sub O times max of 0, Q minus D plus C sub U times max of 0, D minus Q. That's the engine of the model. Okay, now we take expectations. Averaging that cost over the demand distribution basically turns the two max terms into two integrals. Overage weighted up to Q, underage weighted beyond Q. To minimize, we differentiate G of Q and set it to 0. The derivative tidies up into C sub O times F of Q minus C sub U times the quantity 1 minus F of Q. Set that to 0, rearrange, and you land on the headline result. F of Q star equals C sub U over the quantity C sub O plus C sub U. And that, is the critical ratio. And what is that critical ratio really? Well, F of Q star is just the probability that demand lands at or below Q star. In plain English, the critical ratio is basically the chance of satisfying all the demand if you order Q star units. It's a target fill probability and it leans only on the two costs, nothing else. All right, numbers time. For Mac, the overage cost, that's, buying the journal but not being able to sell it. In other words, we've got oversupply. A C sub O is 25 minus 10, which is 15 cents. The underage cost, basically not having enough journals, C sub U is 75 minus 25, 50 cents. Plug it into the ratio, 50 over 15 plus 50, which is 50 over 65, about 0.77. And that tells Mac to stock enough to cover all weekly demand 77% of the time. Put another way, the optimal order is the 77th percentile of demand. Mac should buy enough copies to satisfy 77% of the total demand. Now, how do we turn that 77th percentile into an actual copy count? We use Q star equals sigma Z plus mu. That Z is, read from the normal distribution table. How many standard deviations above the mean we got to sit to capture 77%? On the picture, the shaded region under the curve, the chunk left of Q star, is exactly 0.77, and Q star sits just right off the mean. For Mac, it's 4.74 times 0.74 plus 11.73, about 15.2, which we basically round to 15 copies. All right, where did that Z of 0.74 even come from? The table gives the area between the mean and Z, so we first subtract the half below the mean. 0.77 minus 0.5 leaves 0.27. Then we hunt the table, for the entry closest to 0.27 at the row for 0.7, column 0.04. That lands us at z equals 0.74, basically 3/4 of a standard deviation above the mean. Now here's a nice gut check. What if we swap the costs? Overage 50 cents, underage only 15. And now leftovers hurt more than shortages, you know. The critical ratio flips to 15 over 15 plus 50, about 0.23, just 23%. A lower ratio means a lower target and the z goes negative, minus 0.74 this time. Q star becomes 4.74 times, minus 0.74, plus 11.73, roughly 8.2, call it 8 copies. We order below the mean now, which makes sense. All right, same table trick, just mirrored. This time the target is below 1/2, which means we take 0.5 minus 0.23, leaving 0.27 again. Same 0.27, same magnitude basically, but because we're on the left of the mean now, the z comes out negative, minus 0.74. And that negative z is exactly what tugs the order beneath the mean. All right, last stop. What if we ditch the normal and just use max empirical distribution directly? We still need that same critical ratio, 0.77. We read down the cumulative column, f of q basically, for where it crosses 77%. It lands between q equals 14 and q equals 15. And with a discrete distribution, the rule is always around up, which gives 15. 15 copies, exactly what the normal said. 2 different roads, same destination. All right, that's the news vendor core. Thanks and gig 'em.